All right, so I promised we'd just do a quick primer on Droop because it's another really important concept for later on. We're going to be talking about voltage control, and that will also have a Droop. So Alex showed this slide here, grid frequency versus power output. So we'll just talk about what is Droop and what's the point of it. Okay, so this is our vertical axis here is power output. So we're talking about a power controller. Okay, so we could think of that could be a governor on a synchronous generator, or it could be a power plant controller on an IBR, but something that controls active power in this case. So we've got a power output is up and down, and the horizontal axis is frequency. Okay, so that's an input into a controller. So the controller is measuring frequency, and it's acting on active power in this case. Okay, we could also be measuring voltage and acting on reactive power, but in this case, we're doing power frequency control. So before we talk about Droop, let's just imagine that this was just a flat line. Okay, so we didn't have these slopes here. We just drew a line straight across from left to right or right to left. And what that means is that the controller is going to look at frequency. And if the frequency is at exactly 60 hertz, the control is going to set to 0 power. Oh, sorry. I should say, yeah. I'm just wondering if this is tipped. So if we go above frequency, if we go to 61 hertz, somewhere out here, we're going to want, oh yeah, we want to tip this whole thing this way. Yeah, okay. Let's go to voltage control Droop for the same. This is going to be exactly the same concept, but this is a little bit more straightforward. So power frequency and voltage reactive power is the same exact concept for Droop. So in this case here, we've got the same kind of plot, but now we have on the right, left to right, we have reactive power. Okay. Inductive on the left side, and in this case, capacitive on the right side. And this one is voltage. So now voltage is the measured input. So we're measuring voltage, the controller, and is going to act on the reactive power. So now we're going to make this flat. So in the other one, we would have had to make it vertical. But in this case, we're going to make it flat. So we're going to say 0 Droop is just straight across flat. And then if we have voltage goes up, we're going to go to reactive power side. Basically, this is going to go all the way to the left, and we're going to go to our minimum reactive power. So as soon as the voltage goes above 1 per unit, we're going to go all the way to the left. So if we go 1.001, we're going to go full reactive power, inductive, and try and pull the voltage down. And if we go to all the way to the right, we would do that the moment that the voltage came down to 0.999. Okay, so very, very sensitive reactive power. So that would basically, as soon as the voltage goes up, you're going to slam against that, and as soon as the voltage goes down, you're going to slam against the other rail. So the voltage gets voltage controller is very sensitive. You can add a deadband if you want, and that's fine. Now that will work, okay? So possibly it will work, but it basically will be just a very, very sensitive controller. If you put it at 0 and you have another reactive power controller right next to it, we really have now 2 devices that are measuring voltage, maybe not at exactly the same place, maybe they're slightly separated, and one of them has a voltage of 1 and the other has a voltage of 1.01. Okay, that's what they're measuring. So if their voltages, the Droops are flat like that, one of them will go all the way to reactive power to try and get the voltage down. And the other one, if the voltage is in between those 2 set points, will go all the way to the other side. And then if they're both actually measuring the same point, and they both have a flat Droop, there's now no one operating point. Yeah, maybe a better way to say that even. I'm having trouble without being able to draw, sorry. I think we're going to figure out a way for me to draw later. But if I draw that line flat and I put the voltage exactly at 1, okay, what should the reactive power be? If we have no droop, this is a flat line, and the voltage is at 1. Where is the operating point? It's anywhere, right? Could be either at that end or that end. All are valid operating points. So the moment and that means that if I have multiple controllers, they all have multiple operating points. They can all float between negative and positive control. The moment I slope that, now whatever the voltage is, I have only a single operating point along this line. If you have two plants next to each other on slightly different droops or slightly different voltage measuring points, they will not be optimal anymore, but they still only have one operating point. So they can't really fight each other. So droop is a very important mechanism for making sure that that there's only one operating point in the system. And you can control how much the plant responds with the slope. So if you make a very low slope, very flat, but still sloped, say 1%, and you have to be careful how you define 1%, like Alex said, then a small change in voltage will result in a lot of reactive power one way or the other, but still only one operating point. If you make it a very steep slope, now it takes a lot of voltage change before you get to the end of that line, right? So you end up with controlling the degree of response with that slope. And it works the same for active power and frequency. So if you have all of the generators on this sloped line, they each have one operating point for each frequency. So if they have a frequency that's slightly high, they bring their active power down by that defined amount, right? And again, you have to specifically define what you mean by that slope, but they're all on that defined point. If the line is flat and you have no droop, that's just called droop, basically. I see a puzzled look.
Yeah, so I'm trying to square this with like a PID control that most of these systems would have.
I'm gonna need to draw.
Part of it is, it sounds like this is like almost open loop control dictating what the reactive power set point would be. But it also sounds like a way to decouple two systems that might otherwise be coupled through this one point or very close points.
Okay, can I share this? Okay, so there maybe I'll figure out a slide later. I'll draw you a slide how this works in the control loop. So what this is you would add this control into if you're doing a PID controller or a PI controller, you can add a droop parameter back. It's a feedback gain from the output of the PID back into the summation block going into it. Okay. So that adds into the error for the PID. Okay. That is how you implement the droop. But it's basically a defined way to ensure there's a single controlled operating point in response to an output. So it determines the degree of response, but it also will ensure that two plants next to each other will not be able to hunt. They only have one place they can be for a given voltage. Okay, if you set the droop too narrow, then you have problems with measurement and oversensitivity. They can start to fight again. So typically for voltage control, we don't like to go below, for example, 2% droop. But if you set it to a very high percent droop, 10% or something, you'll get very little response. Everything will be kind of dead because you don't have, it requires a large change in voltage before the plant responds.
So what you're kind of doing with it then, if you're kind of biasing your feedback?
You are adding in, the way that you do it is you add in a measurement or in a bias in the controls to the error based on what you're actually doing. That's not an easy way to just talk about it. I'll show you on a control block diagram. But yeah, conceptually is what I want you to understand, is that it's ensuring you have a single operating point and determining the degree of response to a given change in steady state. And this is a steady state controller.
Yeah, it gets a lot more complex when the voltage set point continues to move every time you change reactive input. I think you mentioned it briefly, but deadbands can also help with the hunting, right? If you have a little bit of deadband, which simply is just an acceptable amount of error.
It's
It
literally a
helps you.
place where the controller stops listening. It's a dead
Yeah.
section in your
Yep.
controller.
And that also helps the hunting. So if you have a little bit of deadband, you have a little bit less propensity to have control interactions like he's mentioning. But using deadbands and slopes together are really important.
And it's important to know that these droops, whether it's frequency control or voltage control, this is all where it will settle. In the short term, everything can respond how it wants. So you can have two controllers that are very different response times. One of them comes in really fast and the other comes in really slow, and they'll push each other around on these droop slopes. So if you're not careful, you still can make them fight, but most of the time a droop, at the end of the day, once everything settles out, it will define what the output is so that they're not allowed to be on hunting points in steady state.
And the pushing around aspect of it will get worse as the system's strength reduces as well. Like a very strong system, very firm voltage. If I'm a 100 megawatt wind farm, I'm probably not cranking the voltage of the system around too hard. If the system strength is strong, if it's weak, then I can move the voltage pretty substantially, which means I'm giving everyone else a different measurement to go on. So if you have like a really weak grid, you probably want a less severe slope, like a higher percentage of slope, less response, or maybe a larger deadband.
Right.
Yeah.
So in this section here, this is our deadband for frequency power control. In this area, there's no one defined operating point. Basically, your power output will stay constant for any frequency, while there is no one frequency for given power. So everybody can do their power, whatever they want, as long as the frequency is between plus or minus, say, 36 millihertz in either direction. And as soon as the frequency hits that bottom limit, 59.5, let's say it'll be out here, everybody has to be changing their power by a certain per unit amount. And that amount that they change will be governed by this slope. And the same in the other direction. All right, back to you.
Great. That was really good intro, because it's really hard to describe what it does and how it works, especially even for folks who've been doing it for 20 years or more than 10 years and others. It's even difficult for me to describe slope and droop and why all that works together. So it's really important when you're doing interconnection studies to just test it, right? All the things we talked about. If you're using a good model, even just a generic model, they have voltage slope, frequency slope, droop controllers in there with logic. It's much easier to just run one, right, and see what it does. If it does what you were expected by measuring what you expect, than it is to kind of guess and do the math and figure out exactly where your operating points are.
Yeah, and the nice thing about droop for commissioning plants or measuring plants when you're in the field is that's a very measurable thing. You can just look at the Q or look at the active power and measure the frequency or measure the voltage. And then it's a simple calculation. So it's in steady state. You can measure what the droop is. So that's a very nice data point for validation.
Yeah, all of these normal operating controls, so active power set points, reactive power set points, which we'll talk about, all the droops, those are all things that you can test on a live system, right? So those are things you can test and verify during commissioning and compare them against your models. They're all kind of small disturbance, small signal type things that you can test in the field without making your operators too angry with you when you're doing that. So take a quick breath and jump right into reactive power controls. We'll probably skip a lot of the droop discussions. We just did it. But why do you have them? Maintaining voltage levels at point of interconnections, significantly more location dependent than frequency, obviously. And maintaining this voltage at all these numerous operating points to keep them near normal is when you have all these interactions with controllers or system strengths, or the system here at this location and the system at the hotel may be slightly different strengths. Maybe it's too close, but so like voltage control here might be different than voltage control needs over there. So like managing all of those local points, really specific pockets of voltage or system strengths or things like that, you will get a lot of variability in what is appropriate for voltage slope control. So where frequency droop, you can, a lot of utilities and regions will just say, for this region, you're at 5% droop, you're at 36 millihertz, and we're okay with that because that's what we studied our system. It's really much more regionally specific for voltage. A lot more opportunities to do the wrong thing for voltage. Even if it's a really strong system in a weak pocket, you may have one machine who's tuned the same as everybody else, who just has a really weak point of interconnection, and they're just oscillating or forcing themselves into mode changes or giving other people problems and things like that. So very local, very variable. The discussion we just had, which is confusing in its own right, that's again steady state. If we assume the voltage is super, super strong, you can get an operating point. But in reality, as soon as I start, if my system is somewhat weak, as soon as I start moving reactive power, my voltage is changing. So now my operating point changes every single time I sample, right, for the most part. So when I say maintaining specific voltage at TSO discretion, there's a little bit of an operations piece, right? So if you're a developer, you may notice, right, if you're interconnecting in different areas, even in the same region, you're going to get different nominals at your point of interconnection, right? If, on one side of Texas, it might be 3%, one at 1.03, and others, it might be 1 per unit. And certain parts of like MISO or the middle of the country, maybe 1.05 or something. And this is done just because that's how the system needs, what the system needs. There are some operators who use that as kind of a way to compensate for voltage drops when transferring power over certain areas. So very important when you're doing your studies to make sure that you're using the right nominal point when you're doing your voltage loops, because then that offsets the entire curve, right? Your nominal is different now. Your nominal would be, if your utility says you're operating at 1.03 and you better not go outside of 1.06 and 1.0, that's your whole voltage slope curve got shifted. And you need to kind of test and tune or do the math or ask your manufacturer, which voltage slope settings do I need to make sure I'm not making my utility angry by going outside my band without operating too quickly or too slowly or anything like that. And maximizing reactive power capability is also a piece of reactive power controls. If you have a maybe misparameterized slope and you've saturated in one direction or the other, you don't have any more capability in that direction if a fault happens, right? So when you do these voltage slopes, you probably want to pick a point where you're not always going to be saturated on one end or the other, so you're not at maximum injection or absorbing, so that there's stuff there, the reactive power there for support if a fault happens. And that also means choosing appropriate control modes, especially for reactive power. Because when we say reactive power control, it's not just one thing. Well, I guess it's more than one thing, but so is frequency. But frequency was just two reactive set points. It was active set points in PFR. For reactive power, we have reactive power set points, power factor set points, automatic voltage regulation, which is the slope and droop conversation. But these may not all be operating one at a time, right? They may have these overlap on top of each other. So you may have an automatic voltage regulation with a power factor limit, which means you're, let's see, this curve is, the bounds on the end is exactly this curve, right? So this is a power factor limit. You have 9.5 power factor max and min, but you may not have that limit. So when you're making your requirements and trying to figure out what you need to do, it's very important to know what are my reactive power capability, like the requirements for reactive power capability, what modes do I need to use to make sure I can do it? How do I enable my plant to be grid friendly? And we can talk about what grid friendly means. But so reactive power set point, we'll go quickly through this since it's very similar. Secondary, tertiary time, the same as active power set points, you just change your reactive power. There's a little bit difference there. I mean, it should be somewhat similar as far as the nuance of active power set points during a frequency disturbance, but there's a little bit less overlap between those two control modes a lot of the time. You also have power factor set points, so it's just like reactive power, but instead of saying give me 10 megabars, you say give me 0.98 power factor lagging. So very similar, different control loops, same responses. You're moving your reactive power to something you you specified or asked for. And then automatic voltage regulation is pretty much the proxy to primary frequency response on the reactive power side. So your reactive power is changing. It's a function of the difference between the measured and what you're supposed to be operating at. What you're supposed to be operating at is different depending on where you are and who you're interconnecting into. But then we have open and closed loop controllers. Open loop controllers, they don't care about any feedback. They're just doing what they're going to do based on their measurements, which may be unstable in a lot of grid conditions. If you want to use open loop controls, you really kind of need to tune the entire system together. in a way that you don't cause control interactions or any adverse things. But we're going to focus a lot of here on the closed loop controllers, because these are the ones that are pretty much most often in use, especially in the US. And these incorporate feedback to minimize those large swings, right? So you get some feedback back from what you're actually doing on the system, so you're not just kind of massively ramping to either side of your controls. So power factor control, really simple. The left side, this is a dual purpose diagram, I guess. The left side, power factor, we all know what that is. So basically all it is you would have an operating point from your utility that says operate at this power factor, and you do that, right? But you'll see the red line, little red dot with the lines, says power factor control means that your reactive power output is proportional or dependent on active power production. As active power comes down, so does your reactive power. So it's not just a certain set of megavars for the nominal. It's whatever active power output there is at the moment, you have a certain number of vars to provide. So really simple control. You could put these as its own control. You can say just operate here. You can say here's a limit or bounds on a certain power factor to avoid equipment damage or other things for system specific criteria. But just really simply, it's just as power changes, reactive power changes, so power factor is the same, just based on the power triangle. It's not one of the best ways to control your facilities, in my opinion, and we kind of saw this as an industry with Iberia and their blackout. A lot of the IBRs were operating in fixed power factor mode, which means not power factor limited, but just fixed, which is exactly what we talked about here as it goes up and down. And what you get is that little triangle, right? So the little orange triangle is a facility that's limited at 9.5 power factor, and the blue is kind of a typical PV plant. And what you see with the red hashed is that's all the reactive power you're leaving off the table when you're using a power factor limited mode. The other piece of this is that's if you're using power factor limited mode, which is slightly better than Iberia, right? Because if you're power factor limited, at least if you're injecting megavars and you need to absorb them after a fault, you could go the other direction just with that bound of 9.5 power factor. If you're fixed, you're fixed. If I'm fixed at 0.98 lagging and an event happens, I'm not absorbing any vars. I'm just staying exactly at that point. And the level 2 alert from NERC, which we put out for IBR performance, about 35% of the IBRs out there right now, the solar PV is in BESS, and you can kind of probably map that onto wind as well, but about 35% are operating exactly like this in the power factor limited mode. And that's due to FERC Order 827, which we'll talk about in a little bit in the why things are the way they are section tomorrow. But again, it goes back to specificity and language, and just very important what that means and what comes out of it. So this is a direct result of a little bit of bad language in a FERC order that pretty much made this operating procedure for a while, and now we have over a third of the resources who are, in my opinion, operating on state or in a not as grid friendly as they could be, let's say, operating point. So reactive power set point, again, really, really similar to the others. It's just you give me a queue. You don't often use this in a live operations setting. Like you very rarely would say, hey, give me a new reactive power unless something bad is happening. A lot of times this is for commissioning, maintenance, testing, other interventions for specific reasons. If I'm trying to push power over a certain line, I might ask you for more vars tomorrow to keep the voltage up, that type of thing. This is voltage droop and slope. I'm just going to skip this since we hit it pretty hard. But this is just a little bit of a different colored diagram where you see this is with the deadband included. The deadband's the green, it's flat. It's just any operating point in there. And then you have different slopes with max. So the other thing to note here is similar to frequency ramps. If you have a really complex IBR, you may have like 3 different ramp rates or 3 different slopes in here. And it's just really important to make sure that when you're asking for it, when you're providing it to someone, that you're all in the same playing field, right? The utility wants one slope, maybe, with one level. They may not want 5 different slopes to get there, but you may have that in there. So just another one of those places where it's really important to keep your language consistent. And you want to talk StatComs really quickly?
Yeah, we can do just a quick sidebar, and it's a good test of changing computers here. We're kind of jumping around a little bit. Alex and I were talking and trying to figure out what what are all the topics we want to touch? Because just about all of these topics, we can go in a lot more depth, right? So we're going to try and take you on a bit of a wild ride of all kinds of topics. Right? So if I just do this, turn this off. That mic, right?
Nope, this, turn that off.
Oh, that was off.
And share the WebEx.
So here, and I can share here.
Yep.
Okay, since we're talking about voltage control, one of the devices that we use for voltage control in the power system, there's a bunch of them, right? We have IBRs, we have generators, we have switch capacitors. We actually have lines that we can switch in and out sometimes. We have voltage controllers on our transformers with tap controllers, but a dedicated transmission level voltage control device is a STATCOM. So when we're talking about voltage control, this is kind of our one of our best tools for dedicated voltage control. So just a few slides sidebar here. When you're taking a voltage, when you're trying to get a STATCOM, you're a transmission planner, let's say, and you want to procure a STATCOM. So I stole just 3 slides from a tutorial we did on STATCOM procurement at the IEEE general meeting last year. So that's my reference. So first we're going to identify the grid issue. We have to decide there's a problem, there's a voltage issue or insufficient control. You might be worried about specific symptoms. You're having trouble keeping the voltage above a certain point or below, or usually when you're deciding on a STATCOM, since a STATCOM is a variable VAR device, it's like a vernier control on voltage, you're able, or on reactive power, you're interested in the dynamic reserve. So you're interested in fault response or controlling voltage that's moving up and down too much during the course of a day. You got to do some studies to decide how much do you need, how long do you need it for, how quickly do you need it, and then consider your different scenarios, and you want to define your objective. So maybe you're trying to keep your voltage, operators are trying to keep the voltage below 1.05 and above 0.95. They're interested in a recovery time. They want the voltage to come up above some level before a time is encountered. And then you might have lots of other things. So I wanted to just give you a couple of things, just pitching STATCOMs here for a minute, because they're a wonderful transmission device that just deal with a lot of issues. So you can, aside from voltage control, you can do things like active harmonic cancellation. You can do power oscillation damping. You can provide degraded modes for the STATCOM, so it can be a highly reliable device. So if you're worried about transmission reliability and the metrics that Alex was talking about, this is intended not. This is usually owned by the transmission provider, so it's designed to help improve those metrics, so they can be highly reliable. They can cancel negative sequence. They can do slow reactive power control, which means on that droop curve, we can actually slide the whole curve up and down around operating points, so that when the voltage sort of drifts higher in the system, you can lift the reference of the STATCOM with the system so that it keeps itself more or less zeroed around reactive power in the slow time frame. So if you're trying to reserve a STATCOM for fast voltage control, you can do that by lifting and lowering that whole droop characteristic, right, within limits. It can do supervision of stability, so it can actually change its gains in some cases. It's not always a desirable feature, but you can actually have it change its gains. You can coordinate between multiple ones. You can do manual VAR control, like Alex was saying, flicker control, black start energization, and grid forming. Nowadays, we do grid forming. So the reason why I wanted to show you this sidebar is just because of this figure, which shows you an actual capability curve. So this is that same voltage control curve that Alex was talking about, but now you can see where all of these points come from. And when you're designing a StatCom, and StatCom I'm using as an example, any voltage source converter based device like an IBR can probably do many of these things, but StatCom is nice because we know we can very, very clearly specify every point on there and decide when we want to use it and why. So each of these points, for example, let's start with the middle. So on the bottom of this plot, we have, now this is the way StatComs are specified. They go the other way from Alex's plot, but capacitive is usually on the left and inductive on the right. So it just means that the slope is facing the other way. And that's the droop, right? So on the in the middle, we have our nominal voltage, and as the voltage rises, we're going to be moving to the right. So my right, your right as well. I'm pointing to your left. Okay, so we have to define the capability of this device at each of these points. So A is a capacitive design point. And keep in mind on the bottom, we're not talking about reactive power, but reactive current in this case. So we use this IV characteristic, current versus voltage. On the left side, this point C is our continuous capacitive high voltage limit. And that is going to be a cost point for the StatCom because that's where your current is defined in the transformer. We have to be able to sit there all day long. And if your current is above, or if your voltage is above nominal and your current is constant, your reactive power is above nominal. So if you ask for 100 MVA StatCom, megavar StatCom, that would be defined at nominal. As the voltage goes up, you're going to get more megavars, right? So this C point is actually the cost, one of the main cost points for the StatCom, because that's your transformer ratings. And then you're going to go flat across here until the middle point. Maybe this is 1.05. And then you're going to see your droop slope kicking in until we get to point D, which is the continuous inductive limit. And now we're on the inductive side, so the reactive power is going into the StatCom, and your terminal voltage of the StatCom is lower. It's not a design point. So this one, they can usually give you more or less what you want. As you hit the final limit here, this maximum voltage set point, maybe that's 1.1 or something, the StatCom just stays pulling reactive current at its limit until you get to some design point G, which is going to be limited by the valve itself. So that's how much voltage is allowed on the StatCom valve. Okay, so that's another cost point, but that might be fairly high voltage, 1.2, 1.3, yeah. Yes, exactly. But most of these design considerations are not at the high side. So this is the specification for the transmission planner will say, I want you to be able to ride through point G, let's say 1.3 per unit voltage continuously, or at least for a short period of time, and pull the voltage down at that point. That's how they specify it, because that's what they know. But when that specification goes to the vendor, and the same with when you go to the IBR vendor, they need to translate that through their transformer to their terminals, and that's going to be a different curve. The whole curve is going to be sloped, and that will be significantly wider voltage ranges, but that will be the actual design limit inside. So based on this, they will translate that through their transformer into the low side, and then they'll figure it out from there. And then you get down on the inductive side, you come all the way down to the minimum capacitive short time, and this is limited by auxiliaries usually. So at the very low end, like Alex was saying, there's all this other station equipment that has to also ride through the plant. The valve might be fine, but there might be cooling and other things that can't sit at 0.2 per unit for longer than, say, a second or something like that. Okay, I saw a question in the back. Absolutely, go for it. That's not true. There's lots of dumb questions. I'm just. Sorry, could you say again?
The qualities you're describing are very, right? lots of things to stabilize.
Right.
And so what would be the reasons that a transmission owner does not put a lot of these in place? How expensive are they? And also, if you are looking at this we're looking at interconnection studies,
Mhm.
this seems like that would be a potential result that someone could pay for instead of a transmission.
Right.
So maybe that's where you're heading. I was just curious about.
Yeah, and I'm not going to spend a lot of time on it now, but you're touching on a few really important points. So one is that a STATCOM is just another tool in a toolbox, and actually for many years, including Vestas, while GE held a patent on voltage control for wind farms, which was one of the most insane patents I've ever seen, Vestas had to install a bunch of little STATCOMs alongside their very capable voltage source converters. So they had wind turbines that could do this. They had the same capability, but they were constrained by patents. They couldn't do it. So they built STATCOMs alongside with their plants, and those went into service all over the place. How much do they cost? Why wouldn't you use them all over the place is a great question. They're actually wonderful devices, but they're not cheap devices. Usually they're owned by transmission companies because they're solving a transmission problem. They take between 2 and 4 years to procure. Did you have something you wanted to add on that?
I was just gonna also add that as they get bigger, they get much, much more expensive. So like what's the average size for a
These
stat?
days?
Yeah.
Let's go back to the old days.
Yeah. Okay.
So the thing that's changing now is the data centers, right? And so suddenly we're going to have we'll talk a lot more about this on Wednesday, but we're having a lot more trouble with voltage control. And so STATCOMs are coming in and they're very big. In the last couple of years, this is even pre-data center. 2 years ago, we did testing on a 2 times 400 MVA in California, but lots of them are hundreds of megabars, I would say. Yeah. And I won't talk about prices. You can reach out to some OEMs, but it's not cheap. Like Alex said, you're in the tens of millions of dollars for sure.
Yeah, before they were very large. You're more like local support, right? Because it's you get a limited amount of bars, so you're kind of solving a more local problem. If you can get a massive one, then you can solve bigger problems too. But obviously, the cost goes way up.
I think that's all I had on this, Alex. So
sure. And to your other part of your question, you also mentioned, this could be the solution. A STATCOM could be the solution from your study, which. Are you plugged in?
I just noticed I can draw.
Oh, great.
That's good.
That's amazing.
That makes me happy. Okay.
Yeah, and just while I plug in here, because they're expensive and because they could be the result of your interconnection study, it underscores the importance of actually using the right models and studying your plant the right way, because it's often much, much cheaper to tune something or use a different model than it is to buy a STATCOM, just in general. And I've done that firsthand a few times in my career so far. So let's see. I'll hit this quickly since we're getting done with the normal operation. So we talked about it earlier, but these kind of inertial controls or primary controls, they're automatic. They only work if they're they're there and they're available. What do you need? Microphone?
My coffee.
Oh, I moved it away from the. I don't trust myself not to smack it over. They need to be there, right, and be studied, and you should be sure that they're going to do what they're supposed to do because they're automatic, right? So, and I just kind of led into it by accident, but these both really depend on quality modeling and quality study work, which means you need probably real code models from your vendor. You probably need, maybe not real code, but some sort of vendor specific modeling. You need to do the studies, the right studies, to test the right modes in the right domain, simulation domain, with the right models. Because when you're expecting these things to operate and they don't, that's when you have real cascading problems, right? So just to mention that, to do all of these normal operation things, I've said it before, and I'll say it probably 10 more times this week, you need to study them and make sure they're going to do what they're supposed to do and that they're going to be there, and you need the right models and data to do that. But it's very possible also to just entirely get through the entire interconnection process without doing this level of detail, right? There's certain parts of the U.S. where, and I'll talk about this either tomorrow or later today, is you may not be able to even be allowed to use the models sufficient for testing and ensuring these things in certain interconnections. So you can see that could be a massive reliability gap as we go through there. So I already kind of hit on all of these, but the big piece that we mentioned, and Andrew hit on it again with the SATCOM about keeping it about near zero, based on proper tuning and testing and modeling and confirming performance is a big part of normal operations is posturing for unexpected. You want to make sure that your normal operations are operating kind of near their normal point during normal operations, so they have capability of bad things happen, and so that you have an expected end and beginning to those conditions. So I guess we'll start the next 20 minutes or so. Abnormal conditions. Probably won't get through it, and then we'll hit lunch on time. Yes, sir.
So how often should you be visiting some of those studies? Because like with it changing, all of that work you just did is going to be validated at some point.
That's a very sticky question. Would you like to? You can answer first.
Yeah, it's not a new problem, right? All of the transmission planners know about this, and so they're usually those studies are done routinely, or when something changes. So if you want to add a new IBR plant, or if you want to add a new STATCOM, or you want to change your transmission somehow, transmission system, that will trigger a study process, and that will bring in all of the new stuff into the old stuff, ideally. Now, those processes can get behind, they can be too slow, they can be inadequate in a lot of ways, but it's something that we know. If you change something, you have to study it, right?
This is that, because in my mind, wouldn't you also want some of that information to feedback what already exists?
Yes.
So for those folks, like I got my wind plant over here, it's been there for 5 years.
Yeah.
New solar plant.
This is a problem that, okay, let me characterize this problem. This is where it gets a little stickier. So the guy who hired me, the founder of our company, Garth Irwin, is a wonderful controls engineer and a modeling expert. He will study, and we do a lot of studies in Texas, for example, with subsynchronous control interactions, which is a family of studies where we're interested in system damping and the controls from all these renewable plants. We're not going to talk about it this week at all, but the idea is, I think the EMT course, they're going to talk about it more.
We'll touch it for like 10 minutes on Wednesday, and then the EMT course will dig into it.
Okay, so the idea is that each of these IBR plants is contributing to damping, either positive or negative, in the subsynchronous region. Okay, so when you add a new plant, maybe you have one plant that's terrible. Okay, it's really just injecting a ton of negative damping into the system, but it happens to be stable. Okay, so the system is now stable. This one plant is terrible, but the rest of the system is compensating for the plant. It gets through all the studies, and the whole system is stable. Now, manufacturer 2 comes along, and it's quite a good plant, but slightly bad. Okay, so it just adds a tiny bit of negative damping in that region, or maybe it's not even unusual, it's just a normal plant, but it's the first plant that sort of tips the whole, it's the straw that breaks the camel's back, and the system is now unstable. When you come in from a controls or a systems perspective, like my partner Garth, he will say, clearly we should fix this terrible one. There's tons of room to fix that one. And not try and jump through gymnastics to try and make this new one a super plant to try and compensate for the other one. That's the engineer's approach and the systems approach, which is what we would all love to do. The reality is much stickier, and it's like, you broke it, so you got to fix it, usually.
Yep. And I probably will hit on this again there's a whole section for 2 hours or so of how the paradigm is changing and why and how to fix it. But your specific question is one of those instances where in the old paradigm, the process makes sense. And the process right now still makes sense if you read it kind of without thinking about it too much, right? So if you, there's only kind of 2 places where you catch it, right? It's either interconnection studies through the process, and then you redo a study if there's a material modification, whatever that means, wherever you're interconnecting, right? In my mind, material modification is anything that changes the performance of the facility, which is a much more stringent definition than many have, just for practical reasons. So that would be how you would change something during the interconnection process only, right? Once you hit commercial operation, there is very little you can do to make someone who's connected change their facility, right? Once you've got your thing, you're in a power purchase agreement or whatever, your GIA signed, I'm not opening myself up to more studies because I've already done it. And if I do studies, you might find something wrong and I have to lose money, right? So in a practical sense, that's huge breakdown there. But with the process as it is written now makes sense, right? Because if you look at the NERC standards, like the TPL standards, you're doing a 1 year out, 5 year out, 10 year out, and 2 sensitivities for your compliance assessment. So in a perfect world, right, every year you're doing next year's study with updates that happened in the year prior, right, in a perfect world. And then you're catching those and projecting them out. But those depend on good models and good data. And being able to put what solutions you come up with into the controllers. And I would talk about modeling and the paradigm shifting, but that's a huge gap right now. Is if we're using, I'm gonna cut myself off before I waste the whole time. If you're doing like a generic model and there's only simple controls, they don't match the manufacturer's controls, and you fix something stability-wise in the system, how do you put that into the manufacturer's control? The parameters you change, the control loops you change, they don't have any reference. So like, how do you put something in place in the field that you came up with in the study and vice versa? And then to Andrew's point, personal experience, and this was actually, in, I won't say where it was. It was once its own country, and I lived there. But there was 2 plants, same developer. One breaker away in a ring bus, so fairly close electrically. They interconnected one facility. They interconnected a new facility. The new one was fighting with the old one. The simplest thing would just say, hey, let's tune them both at the same time and change the voltage groups, right, and make it work. But even the manufacturer, the developer didn't want to change one set of parameters because it opened them up to liabilities. So we literally tuned this other one all the way, like we've tuned to fix it. We tuned around the other problems when the easiest solution was just to open them both up and tune them together. But that expands too, right? And that gets into like cluster studies for interconnection studies, right? It's if I have 10 plants in a cluster study and one of them has bad controls, who's paying for the upgrade? Probably the bad controls, but then they get out of the queue, right? And then you do the interconnection, the cluster study again. And then, the upgrades are there. And but depending on the models, those upgrades might not even be real, right? There's opportunities, and I say it a couple of times, but like conservative, wrong modeling isn't conservative or optimistic. It's just wrong. It could be either way. So you may be leaving the queue for things that aren't real. You may be staying in the queue for things that aren't real. So it's just really messy. But the process as it's written makes sense, right? Redoing a study every year and projecting it every year and all of that makes sense. But in practicality and like pragmatic usage and the legal aspects and the money aspects of it, it kind of breaks down pretty quickly.
Yeah. Maybe one of the takeaways is just that as engineers, we really want to optimize the system. We want to make sure that everybody's behaving optimally. The practical problems, and I think was brought up earlier, that it's very, very practically difficult to retroactively change things. And like Alex was saying, it doesn't make sense to apply retroactive standards. That means in reality, we have to live with bad old equipment or wrong old equipment or suboptimal old equipment and fix it with the new. Even though that might be overall more expensive, it might be even infeasible sometimes. That's the reality of where we are because it's so hard to go back and change old stuff.
Yep, I guess we have 10 minutes before lunch. Before we start, there's any questions? Maybe we can have a little discussion for the last 10 minutes and start this one after lunch, or we can just start this for a few minutes. Hey, go ahead.
You mentioned very quickly that sometimes you can't legally use the model data studies. Are you talking about just like copyright type of trademark?
I'm talking interconnection-wide modeling requirements, and there's like 10 slides and lots of words on that later on. But it's a huge problem.
Yeah, that's what I think that would be.
Yeah.
It would compound everything you're describing.
Oh yeah.
You can't use right stuff. You've got that equipment out there. You can't retrofit things. Like you're putting together a list of.
Yeah, part of my job at Vestas was going around begging to use the right model. That was literally my job, was to go to each utility or ISO and say, please let me do the right thing, please. But yeah, that comes in there's a big section on that specifically. I saw a hand. Yeah.
Yeah, to go back to StatComs, do you have kind of off the top of your head any examples on StatComs kind of, did make it through the process? And you had a lot of reasons why they don't get them by you. Just because there's always a cheaper option.
Statcoms are have a special place in the planning process because they're usually procured as a transmission asset. So it's like a new transmission line or a shunt capacitor that the planners will basically build into their transmission plan. They're not usually associated with a specific interconnection project. That is changing a little bit with large loads, I would say, and it has occasionally been there with IBRs as well. But usually it would be like, we're building out our transmission system to accommodate IBRs, and so they do kind of a special study surrounding that StatCom to try and bring that in. And it's a little bit separate from all of this interconnection stuff. It's not an interconnection, like it wouldn't be defined under the FERC interconnection process, for example. So it's kind of separate. If it is part of an IBR interconnection, which it is sometimes, that is defined in IEEE 2800 as, what do they call it?
Supplementary.
No, like the device that's in the plant that's not the IBR, like
Supplementary.
supplemental device. Yeah. So if it's part of a plant, then it gets lumped into the whole interconnection process. But usually the big StatComs are not. And the reason for that is because most IBRs have the StatCom capability built into them. And so there's no real need to install voltage control devices with an IBR because the plants now are essentially voltage source converters, fully rated or close to.
Yeah, I guess to be super clear, when I've been talking interconnection process, most of this has been generator interconnection process. The transmission element interconnection process is significantly different and has a lot fewer tripping points because of what Andrew just mentioned.
So we need to be cautious of it. I think that's going to factor in states.
Yeah. So again, this is my opinion, and what's happened with occasionally when FERC or NERC steps in, especially FERC, is that they will usually have stakeholder process. Like they'll have the renewable folks who are saying we can't connect quickly enough, or we don't feel like this is true open access, for example. They're upset, and so they talk to FERC and say this is taking too long. We're bogged down. We don't have what we need to get connected. That feeds back into this, and FERC will just basically put deadlines on things. They'll say you have to do this, and you have to study it. You have to get it connected by a certain amount of time. I feel like when you go far enough back, sort of stepping far enough back, what it looks like to me is somebody has to make a reliability sort of holistic decision. Are we prepared to accept the risk of not having good models, of not having good studies? That will trickle all the way back up to reliability. And then we have risk of blackouts. We have risk of, other problems. And that balance isn't always thought through when FERC steps in. So they're thinking about all the stakeholders. They're worried about generator owners and even about transmission providers. But there are physical limits at the bottom of the chain. We can't study things quickly enough. We don't have the right models. If we want to do it to the traditional standard of reliability, we're going to have to take more time to do it. But there is no more time. And so if you force it faster, you're forcing reliability risk into the system. And that's what happens, but we don't quantify that or decide whether that's okay or not. So that's the nuclear option, probably why we don't want to do it. I think we have been. Yeah,
Yeah, we almost hit that option last year. Very close, with like 2 days spare for 901 and the NERC board action last year for that frequency ride through and exemptions, and the retroactivity piece was the major sticking point for that. Yeah, it's going to get worse with data centers too.
Is coming, and that's like I'm much more pessimistic about that whole situation. But we'll leave it till Wednesday.
I'm going to be positive.
We'll solve it
I'll
on
be the
Wednesday.
positive one for the first time in a long time. But there's a lot of things we can learn from IBRs for data centers, and there's a lot of similar. Trying to think of a nice word, non-reliability related motivations between data centers and data centers and IBRs. Right, for IBRs, it was clean energy targets, tax credits. So clean energy targets, the utilities, the public folks wanted to get things connected in a certain time. Tax credits, developers wanted to get things connected quickly to get the tax credits. But like Andrew just said, fast and reliable they don't always match, right? It's either what's the thing when you pick a contractor? It's cheap, reliable, or fast. You can pick two of those three things, and we can learn from that if we actually look back 10 years and learn from that, and we can kind of head off those things, because the main problem is, and this will bring us straight to lunch actually, the main problem is vanished. That what was I going to say? It completely vanished out of my brain.
But it was really good.
You vamped for a second, and I'll think about it.
I would even say that fast and reliable are really hard to do together.
Yeah.
Yeah.
Yeah. Well, those targets, I mean, just specifically, I used to run NERC's IRPS, where I would have people come and present their reliability metrics and how to do the right thing and when to do it. And there were folks on the call who said, that sounds great, but I can't. My boss said I have to interconnect this plant by next year, and I have to do it, which is not a good place to be in for reliability. And we kind of saw that play out. There are some like mini nuclear options, right? Because there's a few ways the standards get written from the NERC. It's either the NERC does it through their stakeholder processes, the normal way based on the process manual. That takes a long time, especially if it's something contentious. I mean, was it PRC29 was something like 7 years of total development time before that was finished. And that only got finished because FERC stepped in for Order 901. So FERC Order 901 exists as a thing because the normal stakeholder process wasn't fast enough for reliability. And I have slides, and we've seen many tens of megawatts of disturbances that no one saw in the planning processes, and they kept happening, and they're speeding up. So FERC Order 901 exists because the regular process didn't work. So FERC Order 901 says do it faster with some timelines and some actual deadlines, which got everyone a little bit more motivated for a reliability side. But then you run into all of the other stakeholder-driven process aspects of getting votes and balloting and trying to manage retroactivity and exemptions and all of that. And even with FERC's leverage or deadline or pressure or whatever, we almost missed getting PRC29 ready or done. And the NERC board had to step in at the end of the summer last year and say, here are you get shortened ballot times, you have to hold a technical conference, you have to just get it done. Here are some waivers and exemptions to get the standard done. So that's two ways you can get a standard written, is if the process does it on its own, NERC steps in and speeds up the process, and the process does it on its own. The other option would be if NERC steps in, makes the process, the board steps in and speeds up the process, and you still fail, which we almost did. And then NERC staff writes the standard. And I used to threaten everybody with, you don't want me writing the standard. Because if I write the standard, everyone's mad. Because it's going to be very stringent and, for whatever reason. So that's the third way you can get it done, is if the board steps in, you still miss, and then NERC staff writes the standard, and it just goes through. The fourth way is there's a major disturbance, right? And then there's just all of the public perception in the, like 2003, right, in New York, right? Then standards get written very, very quickly, right? Which is a good segue into abnormal after lunch. But if you look internationally, most international grids and grid codes, they looked a lot like ours for a long time, right? Very similar kind of stakeholder-driven processes, similar motivations, similar things like that. The difference is each of those areas has had their major blackout. Australia, UK, Ireland, they've all had Iberia. They've all had their major blackouts. And those very quickly evolved into very stringent grid codes. Stringent as far as modeling and accuracy, study data requirements, like readiness when you're interconnecting, which are all things we talk about, but without I don't want to say leverage in the negative word, but without the leverage of a massive blackout, it's really hard to shift the whole paradigm of the industry over to what needs to be for IBRs, in my opinion, right? So that's the fourth way, or the fifth way the standards get written is the bad way, which is people probably died, right? And then you're writing it in blood, which is not what you want to do, right? So the goal would be to kind of head it off, especially for large loads, and not do what we did with IBRs, which was ignore them until they couldn't anymore. When I started in planning in New York, we had 2 wind farms and a solar plant, and we just turned them off because they're not going to come here. We're never going to see that much penetration of wind and solar, so just turn them off. We'll plan around them. Now look where we are today. So there's a little bit of that with data centers right now. And if you do that, then you end up leaving a lot of this advanced controls on the off the table or on the table. Same with large loads. They have a lot of flexibility and things that could be used for grid stability or enabling faster interconnections. But if we don't think about them or talk about them or put them into the process and mandate them or incentivize them, they're not going to come. And then we're going to be stuck in this. We're going to follow probably the same path as IBRs, but much more quickly with large loads and the same kind of challenges and missteps for reliability along the way. Mhm. Mhm. Yep. Yeah, ERCOT's far and away ahead. Yeah, ERCOT's really leading the way in the US for that type of thing.
They take a lot of the heat for that too.
Yeah.
And you know, the problem with being first in the industry is that you get to make all the mistakes first. You had a question.
No, I just had a general comment about this whole, I mean, I agree with everything you said on in terms of the process, but keep in mind, this whole SPPTF is gonna be, essentially, turning the whole standard process upside down. It's gonna be completely different going next, well, maybe not next year, but the year after, for sure. Because it's, obviously, as far as we know, it's just gonna go updating the rules and procedure, standard process manual, next year, which will take time. And everybody will, industry will get a chance to vote on it, but, probably my best guess scenario will be end of next year, if the earlier next year, earlier the year of 2027, will be the new process, right? The SPM will be no more.
Yeah, hopefully. Yeah, hopefully. Yeah, I mean yeah. Yeah, I mean the MSPPTF is just producing recommendations.
Correct.
So they still would have to go through the process of updating the thing.
You gotta go through the board trustee.
Yep.
And then, it will get updated to the SPM.
Mhm.
And the industry will, right?
Yeah, in a perfect world, yeah.
I'll say just for the younger folks, ERCOT's its own winner. So it's got a lot less service. So it's small, it's kind of like the lab for interconnections, so that's why.
They also have less, they're not for, yeah, so they have more flexibility and freedom, which is good and bad, depending on how you look at it, right? Yeah.
Yeah. And ERCOT looks to the real labs like Hawaii and some of the skinny systems in the Midwest and some of these other things where they've seen the events 8 years ago or 10 years ago, 5 years ago. They've specified the grid forming, they do all these things, and then ERCOT looks there, and then everybody looks at ERCOT.
Yeah.
So yeah.
And we're